Ladies and gentlemen, it is my great pleasure to welcome you to the presentation, a novel thick ellipsoid approach for verified outer and inner state enclosures of discrete-time dynamic systems, which I co-authored together with my colleague Luc Chelin from Insta-Bretagne in Brest. At the beginning of this presentation, I'll provide you with a motivation how to propagate bounded domains of uncertainty through nonlinear dynamic system models, which are described in a discrete-time form. As a novel contribution in this presentation, we'll show thick ellipsoids, which provide a means to quantify the worst-case overestimation resulting from nonlinearities when mapping bounded domains from one time step to another. This also serves as a basis for the derivation of a recursive simulation technique, which will be shown for linear and nonlinear discrete time system models before we come to conclusions and outlook on future work. Now, starting with a simple linear autonomous system model, xk plus 1 equals a times xk, where a is a point-valued given system matrix, and xk at the initial point of time is described by this unit box. Let's assume that a describes nothing else than a counterclockwise rotation in each time step by 45 degrees. The exact solution sets are described here in the last row of this figure. Now, when performing naively interval evaluations of the system model and replacing the solution at each time step by an axis-aligned box, you will immediately see that the resulting state enclosures will blow up from one time step to the other. And in the worst case, this leads to an exponential growth of the enclosing domains here. The reason for this is the so-called wrapping effect, which results from the fact that the exact regions in the state space are enclosed in each time step by an axis-aligned box, in this case by the blue one in the time step k equals to 1, and by the white one in the time step k equal to 2. For this linear system model, we can eliminate the wrapping effect perfectly by reformulating the simulation in such a way that at each time step, we're relating the outcome of the simulation to the initial state domain by recursively multiplying the system matrices and not by recursively evaluating in a naive form in interval arithmetic the solution from one time step to the other. For nonlinear system models, however, this simplification is not always possible. Let's assume that we have a time-varying system model, gk, depending on the state vector x, some parameters p, and an open or closed loop control signal u. And as I already mentioned here, the system model may be time-varying due to time dependencies k. Now our goal is to determine guaranteed outer bounds for the reachable state domains at each time step k for a given future time horizon. The naive evaluation in solution approach number 1 would be to recursively compute bounds x at a time step k plus 1 in terms of the initial domains at a previous time step k. However, this is prone to overestimation due to the wrapping effect. This wrapping effect can, at least to some extent, be reduced by performing a change of coordinates. This change of coordinates, for example, a linear coordinate transformation tk, usually reduces the pessimism if the corresponding system dynamics are mostly linear or close to a linear system model, and that we can reduce, for example, the pessimism due to rotations of an interval box by a suitable change of coordinates. However, for strongly nonlinear system models, this is not enough. The idea for nonlinear system models would be to perform a subdivision and subsequent merging of intervals to enclose a complexly shaped domain as tightly as possible. In addition, we can perform consistency tests by temporarily backward mapping of solution domains from the time step k plus 1 to the previous time step k. This can either be done by analytic representations of the inverse mapping or by using interval Newton techniques if analytic backward mapping functions are not available. Furthermore, we have to account for possibilities that allow us to combine subintervals again into the union by a smaller number of interval boxes to avoid an excessive growth of the computational effort from one time step to the other. The corresponding technique is shown on the slide. Let's assume that we have the yellow box. The yellow box will be mapped to this potato-shaped region here in a future point of time, and an Eve interval evaluation would lead to the resulting green domain. The width of the green domain can be reduced by using approaches like, for example, Taylor series expansions or monotonicity tests to a tight axis aligned box by the red one. However, the red one is still pessimistic due to the fact that it doesn't perfectly account for the true shape of the solution. For that purpose, we can subdivide the yellow domain, propagate the subdomains individually, leading to the gray boxes. And afterwards, a backward mapping could be performed by extracting parts of the gray boxes, mapping them backward one time step, and checking whether the backward map domains are fully outside the yellow box. If this is the case, the corresponding subbox can be deleted because it's inconsistent with the dynamic system model. Finally, there exist two further solution approaches. One of them would be to reformulate the simulation of the dynamic system model in such a way as to define this iterated evaluation scheme by expressing the solution domain at the time step k plus 1 in terms of the initial state enclosures at the time step k equal to 0, and to apply techniques like mean value form evaluation, monotonicity tests, or even global optimization techniques to this iterated function evaluation. However, this is quite costly, and to reduce the corresponding computational costs, we could perform evaluations on other enclosure representations like sonotopes, Taylor models, or ellipsoids. However, sonotopes or Taylor models also have to be treated with care because we have to limit the number of vertices of a sonotope that are taken into account in order to avoid a growth of the computational burden from one time step to the other. And we have to bound also the polynomial degrees of Taylor models in order to avoid an excessive growth of the computational effort. Ellipsoids, as they will be considered in the current presentation, now allow us to describe a complex shaped domain, like the green one here in the left half of this figure. We can describe the corresponding green domain both from the inside and an outside by enclosing ellipsoids. This ellipsoid with the corresponding identical shape matrices gamma for the inside and the outside enclosure, and with identical midpoints, will be denoted as a thick ellipsoid with the corresponding stretch parameters rho underline and rho overline given on the slide. Now our goal will be to map the corresponding green domain from one time step to the other and to represent the exact mapping again by an enclosure from the inside and the outside. That means by a thick ellipsoid in the new time step. For that purpose, we have to define thick ellipsoid operators which account for addition, multiplication, subtraction, and division, union and intersection operators, where both of the operands are described by thick ellipsoids. And we should also be able to perform thick ellipsoid function evaluations, where the argument of a function f will be described by a thick ellipsoid. The corresponding outcome should again be a thick ellipsoid that encloses the true solution set from the inside and from the outside. Now, this is being performed in a recursive manner in the frame of this presentation. We do not perform the evaluation directly from one time step k to the next one, but first of all, we will perform a change of coordinates in which an ellipsoid will be transformed into a ball in a multidimensional state space. The ball will be mapped for the linearized system model here from one time step k to the time step k plus 1, leading again to a ball in an axis-aligned coordinate frame. And finally, the influence of resulting linearization errors will be enclosed by this additional ball SB, which allows us to inflate the outer domain enclosure here in such a way that the true solution set is being enclosed in a guaranteed way by the outer hull of the thick ellipsoid in the new time step k plus 1. and to deflate the corresponding enclosure, as you can see it here in light green, such that the inner bound of the thick ellipsoid will be an inner approximation of the true solution set. Now, in order to perform this evaluation, we have developed the algorithm that you can see on the slide. As I already mentioned, it makes use of a point-valued function evaluation to forecast the corresponding ellipsoid midpoint in the new time step. The shape matrix will be forecasted here by a point-valued evaluation of the Jacobian of the system model. And finally, we have to determine the stretch parameters, rho underline and rho overline, in the new time step k+1. For that purpose, we have to make use of an interval extension of the corresponding system's Jacobian, and the other operations that are required are interval-valued matrix multiplications and an extension of a Euclidean norm operator for an interval box. Now, as you can see on this slide, we have managed to derive an algorithm that allows us to avoid costly online optimization techniques, but we are still able to enclose the corresponding true solution sets from the inside and from the outside by a thick ellipsoid. This is now being shown also for some numerical simulations. The first simulation example is a linear system model, which serves as a controlled, or the model of a controlled wheel suspension system, where the only uncertainty in the system model is related to uncertainty in the initial domain, which is described by a thick ellipsoid. The corresponding inner thick ellipsoid bound is being propagated here by the blue lines. The black lines describe for each of the three state variables the outer thick ellipsoid bounds. You can see that in this case, due to the asymptotic stability of this linear system model, both the inner and outer enclosures converge towards the desired steady state and the origin. Now let's consider a nonlinear system model. In this time, this is a nonlinear Brusolator model, which serves as a simple model for describing oscillatory behavior in chemical reactions. If we just naively apply the thick ellipsoid simulation technique in this case, you will see that the outer state enclosures here by the black solid lines may diverge after some point of time. To avoid this phenomenon, we can subdivide the initial state domain into, in our case, n equal to 8 subdomains for each of the coordinates, and perform the simulations. The black dotted lines now represent the union over all sub-ellipsoids in terms of the guaranteed outer enclosures. The corresponding inner state enclosures are described here by the blue lines. Now, if this is not enough, we would even be able to perform subdivisions online during the simulation. But however, then also merging of ellipsoids would be necessary. This can be done by using so-called Löwner-Yon ellipsoids, which allow to find guaranteed outer bounds for the union over multiple ellipsoids. Now I'm already coming to the conclusions of this presentation. What you have seen is a thick ellipsoid approach to describe state enclosures, which is being used for a guaranteed simulation of inner and outer state enclosures for discrete time dynamic system models, possibly with uncertain but bounded parameters. Further related research is, for example, the quantification of the reliability of linearization-based stochastic estimators, like the extended Kalman filter. We can derive specialized implementations for quasi-linear system models. We can use the corresponding thick ellipsoid approach to derive predictor-corrector type state estimators, and also to verify stability properties of discrete time dynamic system models, as well as to design extensions for the simulation of continuous time systems. Now, those extensions are already partially published or submitted for publication. The related list of publications can be seen on the slide. Many thanks for your attention.